When we were pressing the nitrogen system, we had an explosion that took out the rocket. I think every test is always a success. Okay, just stop and think about that for a second. An actual explosion rips through a test site, literally obliterates the hardware and the lead engineers. They call it a success? I mean, this is the intense, absolutely explosive reality of modern rocket testing. If you're going to push the boundaries of human spaceflight, you really can't be afraid of a few fireworks. You need this relentless, almost bulletproof mindset.
Welcome to this explainer. I am so incredibly excited to take you through today's topic. We always see those glossy, perfect renders of rockets soaring through the cosmos. But today, we're stripping all of that away. We're going to look at the gritty, methodical, and honestly, sometimes total chaos of how revolutionary space hardware is actually developed. Specifically, we're diving into the crucible of innovation that is SpaceX's Starship V3.
Okay, let's dive right into this. Here's our roadmap for today. We'll start with the iterative flight campaign, then look at engineering the V3 hardware, head right into the trenches with the pad operators, unpack the paranoid engineering mindset, and finally, wrap up with unlocking the solar system.
So, starting off with Section 1, the iterative flight campaign, from failure to catch.
Now, Starship is a vehicle of just unprecedented scale, but the team didn't just wake up one day and decide to build a towering 400-foot rocket. No way. If they had tried to jump straight to a Mars vehicle right out of the gate, it would have flat-out bankrupted the company. Instead, they had to build a foundation. They cut their teeth on smaller, crucial building blocks first. The Falcon 1, the reusable Falcon 9, the Dragon capsules for both cargo and crew, and of course, the Falcon Heavy. Basically, they had to learn how to do rockets their way just to even earn the right to work on Starship.
Now, what's really interesting about this slide is the sheer, mind-blowing velocity of their progress. Just look at this timeline. Flight 1 got off the pad, but, well, it ended in failure. But then by Flight 2, they achieved ship separation. Flight 3 nailed the boost back burn. Flight 4 gave us a successful water landing. And then, this is the crazy part. Just 5 flights into the program, they returned a 230-foot booster to the launch site and literally caught it midair with giant mechanical chopsticks. I mean, they essentially caught a flying skyscraper. That right there is the pure power of rapid, integrated testing.
Moving right along to Section 2, engineering the V3 hardware, the clean sheet design.
So with all those early flight lessons in hand, the team didn't just patch things up or do a minor upgrade. They went for a complete, clean sheet design. If you compare the early V2 Raptor engine on the left to the new V3 on the right, you can see the design has been drastically simplified. The engineers worked tirelessly to consolidate the hardware, and in rocket engineering, complexity is the absolute enemy. Fewer parts means it's lighter, it's cheaper, and it's much faster to produce. But most importantly, the Raptor 3 brilliantly proves that fewer parts directly equal higher reliability. The ultimate goal here is to get these rocket engines to behave with the routine, boring reliability of commercial airplane engines.
1 million. That is the square footage of the Starfactory facility currently being built to produce these ships and boosters. To put that into perspective, it's just massive. They didn't build a factory this giant just to win some Guinness World Record. To truly build a fleet, they need production capabilities that look a lot more like a high-speed automotive assembly line than some bespoke boutique aerospace lab. And why does this matter to you and me? Because mass production is quite literally the only way space travel ever becomes routine and affordable. The giant scale here is absolutely no accident.
All right, Section 3, pad operators and daily chaos, life in the trenches. So, what does it actually take to test this hardware on a daily basis? Well, it requires a culture of extreme, ironclad discipline. Preparing a vehicle for its first operation isn't a quick check. It's a grueling 12-hour day. Operators have to configure the vehicle, and then they load literal tons of liquid propellant that's been chilled to roughly 80 Kelvin. Actually, to make that relatable, that is a staggering negative 315 degrees Fahrenheit. It's unfathomably cold. Then they execute a whole suite of test cases to check for thermal stress, and finally, safely offload it all. It's this methodical, exhausting daily grind that just has to be flawless before a rocket ever even thinks about leaving the pad.
And the human element of all this? It is intense. As one operator perfectly put it, T-4 on is when my heart rate really starts to tick up. Because at T-40 seconds, they stop interacting with the pad. The vehicle is completely on its own. You can literally feel the skyrocketing tension in the room. I mean, they are about to unleash unprecedented pressures and temperatures on entirely new hardware. The stakes are incredibly personal for the team sitting there running these consoles.
And, as you might guess, things don't always go to plan. Take the Booster 19 static fire attempt, which, by the way, is when they ignite the engines but keep the rocket pinned securely to the ground. So they lit 10 engines, but suddenly an unplanned pad side abort was called. A sensor tripped, causing this hard, incredibly fast shutdown that mechanically damaged 5 of those engines. Now, did the team just pack it up and go home? No way. They immediately removed all 10 engines for troubleshooting and just backfilled them on the fly with hardware from another booster, Booster 20, just to keep the campaign moving. It just goes to show you, operators have to be ready to instantly pivot in the face of total chaos.
But sometimes, the setbacks are a lot larger than a swapped engine. Consider the Ship 36 anomaly at the Massey's test site. A composite pressure vessel, or CPV, exploded. And it didn't just take out the rocket, it destroyed a whole lot of the test site infrastructure. But here's what's fascinating. Here's how they frame this. Losing a rocket is one thing. They have an entire production line for that. But losing the physical launch pad? That takes months to repair. So this failure forced them to spend months completely rebuilding a pad from scratch with new systems, ensuring that the next time there's an anomaly, and there will be, the pad can take a beating and survive. Every disaster is really just a very strict teacher.
Which brings us to Section 4, the paranoid engineering mindset, predicting failure.
So how do you actually survive the daily chaos we just talked about? You adopt a very specific, intense psychology. Only the paranoid survive. A rocket generates just an enormous, staggering amount of data. And this mindset, it isn't about fear. Rather, it's about extreme diligence. The team genuinely believes that when something fails, the clues to that failure were already hiding in previous operational data. If you're good enough, and honestly, if you're paranoid enough to scrub that data relentlessly, you can predict and prevent the next disaster. The answers are always hiding in the margins.
But that intense paranoia is perfectly balanced by this unshakable confidence in science. When outsiders look at this and say what they're doing is impossible, the engineering team has this brilliant, simple rebuttal. Things being impossible is really to be determined by breaking laws of physics. We are not breaking laws of physics. And that perfectly captures their technical mindset. Unless a design literally violates the fundamental laws of the universe, it's not impossible. It's merely a complex engineering challenge just waiting for a solution. They're just trying to leverage physics as effectively as they possibly can.
And finally, Section 5, unlocking the solar system, the ultimate payoff.
All right, we've looked at the explosions, the 12-hour shifts, the extreme paranoia, but what is it all actually building towards? Let's zoom back out from the trenches. It all builds towards this: propellant transfer. Make no mistake, this is the single absolute core technological capability needed to unlock Starship's true potential for deep space missions. Because the vehicle is so incredibly massive, it uses most of its fuel just getting into Earth's orbit. So to go any further out into deep space, it literally has to be refueled while orbiting the Earth.
Think of it like a giant puzzle. Once you master the V3 hardware, you reach orbit. Okay, great. Then you prove you can loiter in space for 48 hours. Check. Then, you demonstrate meeting up with other ships. But once those ships actually connect and transfer thousands of tons of super-chilled propellant right there in the microgravity of space, wow, everything changes. Mastering orbital propellant transfer is the master key. It puts the entire solar system right on our doorstep. It turns lunar access, moon boot prints, and Mars cities from some distant sci-fi dream into a tangible operational reality within our lifetimes.
We've seen the simplified hardware, the fiery explosions, the incredibly dedicated operators, and the sheer massive scale of this vision. The journey is wild, you guys. The highs are incredibly high, and the lows are deeply, deeply challenging. But it brings us to a final, profound thought that I want to leave you with today. If the laws of physics aren't being broken, what is truly impossible for humanity? Thank you so much for joining me on this explainer. Keep questioning, keep learning, and I'll catch you next time.